be with you like a forever chemical. I wanna be with you like a forever chemical.
Hi everyone, I'm Craig Butt. I'm an application scientist at SCIEX, and welcome to the inaugural episode of Dr. Craig's PFAS Fireside Chats, a podcast series where we talk about the challenges and opportunities of PFAS analysis. Now for my inaugural guest, I could not think of anyone more perfect. She was there with me when I began my journey into PFAS way long ago during grad school. Professor Cora Young from York University, environmental chemistry professor. She is one of the OGs, the gurus of PFAS atmospheric chemistry. But certainly her research spans much more broad than that. All things halogenated, all things atmospheric chemistry. She was named one of ACS's Talented 12. She was my collaborator, my co-author, and my friend, Cora Young. Cora, welcome to the show.
Thanks for having me, Craig.
Thank you. So Cora, we've got you on the podcast today to talk about your recent paper that looked at short-chain PFAS in Arctic ice cores from the Canadian Arctic. Mm-hmm. Now tell us, what were your main findings?
Yeah, so ice cores are a really useful tool because they preserve a long-term record of atmospheric deposition. So we were really using these ice cores to see if we could understand trends in deposition of PFAS, including these ultra-short-chain PFAS. And what we found was that around 1990, we saw a dramatic increase in these ultra-short-chain PFAS, much more so than the other PFAS that we normally think about.
Oh, very, very interesting. So, typically, when we think about PFAS, we think of things like, C8, PFOS, PFOA, longer chain. So tell us more about these short chain compounds. What are they?
Yeah, so these short chains, or the shorties as we call them in my group, they are the shorter chain analogs of PFOA. So they're perfluorocarboxylic acids that have between 2 and 4 carbons.
Oh, interesting. Okay. So, when we think of industry moving to shorter chain compounds, most people kind of stop at C4, but you're talking about even shorter than that.
Yeah, that's right. And so some of these chemicals from the fluorinated industry, the fluoropolymer industry, can actually degrade into these ultra short chain PFCAs as well. But there are other sources of the ultra short chains, and those are CFC replacement chemicals. So CFCs obviously were banned because of their stratospheric ozone depleting properties, and replaced with chemicals that actually degrade in the atmosphere to form these ultra short chain PFCAs.
All right, so you talked about the source for these ultra shorties, right? We had our traditional source we think of, the fluoropolymer industry, but then also these CFC replacements. How did those come to be?
Right, so the CFCs were banned, as I mentioned, and chemicals that did not deplete the stratospheric ozone layer were introduced. All of these degrade in the atmosphere to form short-chain PFCAs. And the regulation that brought these into being was the Montreal Protocol.
Yeah, that's great, because I remember back in the day, in the 80s, I think, when the Montreal Protocol came to be, right? It was solved a really difficult problem in terms of ozone depletion, but then we had this unintended consequence, right, of generating products which produced these shorties. Exactly,
and what we actually saw from our ice cores was that the bulk of these ultra short chain PFCAs were actually related to the regulation of the Montreal Protocol and the introduction of these CFC replacement chemicals.
Right, yeah, because you mentioned you saw that spike right after the 1990.
Exactly.
Okay, interesting. Yeah. So what are the environmental impact of these ultra shorties?
Yeah, so the ultra shorties are a little bit different than the longer chain PFAS that we normally think about. So we know in our conventional knowledge that as the chain length increases for PFAS, we see greater bioaccumulation. And so we would expect that these ultra short chain chemicals don't bioaccumulate, and yet we're actually seeing them in humans even at really high levels, rivaling PFOS and PFOA. So very surprising. We don't necessarily understand the mechanism, but they are being observed there. And we do know that they're also very phytocumulative, so they accumulate in plants.
Wow. Yeah, no, that is really surprising because certainly industries move away from compounds like the C8 PFOA, right, was done because they have a lower bioaccumulation potential.
Right.
But yeah, from what you mentioned, in fact, that may be counter to what we think. And I think too, the research I had read showed that perhaps those ultra shorties like TFA are partitioning to different tissues than the longer chain compounds, right?
Yes, we're actually, so one study has shown very, very high levels of the C4 PFCA in human lung tissue, for example. Yeah.
Wow. Okay. Yeah. Again, counter to what we would think of with these longer chain PFAS partitioning to blood and other proteinaceous tissues. Okay. So, we've got analytical methods for the longer chain compounds. A lot of monitoring lists go down to the C4 now. So was this as simply, as easy as just adding this to a normal PFAS analytical method?
No, it wasn't. So these ultra short chain chemicals are a bit of a challenge because they're so water soluble, they do not retain well on our typical LC columns. So as a graduate student, I was trying to analyze for some of these chemicals actually many moons ago and had a lot of trouble retaining them on a C18, our normal C18 column. So now with the advent of mixed mode stationary phases that have ion exchange capacity, we're actually able to retain these and analyze these chemicals using LC-MS.
Okay. Yeah. So, chromatography challenges right up front. But what about detection limits? Because again, when I think of the Arctic and remote environments, I think of exceedingly low levels. Did you have any issues with regards to sensitivity?
Yeah, good question. But these chemicals, these ultra short chains are actually present in much, much higher concentrations than the longer chain PFAS. So we're seeing levels in the hundreds of nanograms per liter. So
Wow.
much higher than you might expect, even in a remote place like the Arctic.
Yeah, and when I think of the EPA's drinking water guidelines, 70 parts per trillion, it sounds like you were seeing levels that were actually much higher than that.
Yes, we were.
Yeah. All right. So again, these remote environments, Canadian Arctic, that's pretty far away, and most of our listeners are down here in more southern industrialized areas. So I mean, what would you expect to see in terms of levels down here?
Yeah, so these higher latitude polar locations are essentially our global background. As we get closer and closer to areas with high human population levels, I would expect that levels of the ultra short chain PFCAs are going to increase. So I would expect in most locations near to human settlements, we're going to see levels much higher than we saw in the Arctic.
Yeah, so certainly likely a problem down here, and if not worse. Okay, so we'll get you out of here on this last question. How many people are currently monitoring for these in addition to your group? And what would be your general recommendation for people who are already doing PFAS monitoring in surface waters and drinking waters?
So not too many people are targeting these ultra short chain. Lots of people are doing the total fluorine analysis now, and they're finding lots of unidentified organic fluorine, and it's likely that at least a substantial fraction of that may be made up by these ultra short chain PFCAs. So I certainly think it's worth people considering adding these to their analyte list.
Yeah, absolutely. So you just mentioned something there too at the end that we're going to have to drop and maybe leave for another time, and that is total organic fluorine, or a total organic fluorine burden, maybe tying in some non-target analysis. But I think that's a topic for another podcast. So there you have it, folks. Importance of ultra short chain PFAS, not just PFOA and PFAS. Cora Young, thank you very much for being my first guest on Dr. Craig's PFAS Fireside Chats.
Thanks, Craig.
I wanna be with you